Okay, so in the last video we started looking at Lagrangian mechanics, and we're going to continue that journey today by looking at generalized momenta. So let's just and ignorable coordinates. So let's just take a look for a moment at a particle that's moving in 3D in a conservative force field. So our Lagrangian will be t minus v. So it'll be 1/2 m x dot squared plus y dot squared plus z dot squared minus some potential that is a function of x, y, and z, but not the time. Okay, so we can go ahead and write the Lagrangian equation of motion for x. For example, let's say partial L partial x minus d dt of partial L partial x dot equals 0. And let's evaluate. Okay, the only thing that depends on x is this v. So this, and we got minus sign in front, so this becomes minus partial v partial, partial v partial x minus d dt of, well, I differentiate this with respect to x dot. I just cancel the 1/2 and I'm left with mx dot there. All right, equals 0. Well, we know what this is. This is the x component of the linear momentum. And we also know what this is. This is, including the minus sign, the x component of the force being applied. So we look at that and say F equals, so we can rewrite this as F equals dpx dt. Oh, hey, that looks a lot like Newton's second law. And we can do this similarly for y and z and get the same kind of result. So we can extend this as a vector and say that F equals dp dt. Super. Well, what we can do with this is we can generalize this idea of momentum. We can just say that the generalized, it's a mouthful, that's how we officially say it, the generalized momentum conjugate to the generalized coordinate say q sub k will define that generalized momentum pk to be partial L partial q k dot. All right. So we can go ahead and look at Lagrange's equations of motion for our qkth coordinate. So, whoops. So partial L partial qk minus d dt of partial L partial qk dot is equal to 0. So that will become partial L partial qk minus d dt of pk equals 0. All right, so we can observe that pk dot is equal to Lagrange's equations of motion required that the time rate change of the momentum be equal to partial L partial QK. Like I say, this is sort of a fancy way of rewriting Newton's second law here, but before we were demanding that this be just the potential, minus V stuck in here. Now we're allowing that there could be effective potentials or something like that that are buried in the T. Okay. So that gives rise to the related idea of the ignorable coordinate. All right. So what all that means is if the Lagrangian does not contain QK, then we say that QK is ignorable, or an ignorable coordinate. So let's ponder what that would mean. So let's say that our QK is ignorable. We just worked out that PK dot is equal to partial L partial QK, but if QK doesn't show up in the Lagrangian, then the partial derivative is 0, and then that implies that the conjugate generalized momentum is equal to a constant. So if you have a generalized coordinate missing from the Lagrangian, so if it's ignorable, then the conjugate generalized momentum is conserved. This is an example of a very important but very seldom taught concept called Nether's theorem, due to Emmy Nether. That turns out that one of my dissertation co-chairs traveled on the same boat from Germany to the United States as her. Okay, well, we will touch more on some of the results of Nether's theorem as we go along here, but this is a big key part of it, is if the Lagrangian is missing a variable, then there's an associated conservation law. All right, so let's do some examples of this, just to get some feel for it. So let's say that we have a cylinder. So there's my center line. All right. And we'll say that it's of radius capital R, and I have a mass M sitting on there, just somewhere. So anyway, we'll say that we're constrained to be on the cylinder. And we'll say that we're subject to a force F equals minus KR. Now, so we can imagine maybe a suitable network of springs or something like that. All right. Well, in an analogy, I think you can convince yourself to a spring. I think you can convince yourself that the potential energy for this force law would have to be 1/2 K x squared plus y squared plus z squared. But if you don't believe me, go ahead, differentiate with respect to x, y, and z, and negate it, and you will get the force law back out. Well, our x squared plus y squared here, due to the force of constraint, will always be equal to r squared. Now, if you wanted to, I'm going to be lazy and not bother. But if you wanted to, you could make that r squared to go away just by changing the 0-point energy of your potential energy function. Doesn't matter when you take the partial derivative, it's going to go away anyway. And let's find the kinetic energy, so 1/2 m. Now here I'm going to go ahead and do the 1/2 m v dot v sign rather than putting it all into Cartesian coordinates. So this will be equal to 1/2 m. Okay, so in the r hat, so cylindrical coordinates are definitely the way to go. So in the r hat direction, we will be going at r dot. In the theta hat direction, we'll be going at the speed r theta dot. And in the z direction, we'll be going at z dot. Now, due to the force of constraint, since we're constrained to stay on the cylinder, the value of r can never change, so r dot is 0. And we'll be dotting that with itself. So you'll get 1/2 m times r squared theta dot squared plus z dot squared. All right, so we've got our t, we've got our v. So we can get us a Lagrangian t minus v. So it'll be 1/2 m r squared theta dot squared plus z dot squared minus 1/2 k. I'll leave in the r squared plus z squared, but if you want to drop that r squared, it really doesn't matter. So let's just go ahead and find our generalized momenta here. So p theta would be equal to partial L partial theta dot. So no theta dependence there, theta dot dependence there, just here, differentiate, bring down the 2, cancel the half. We're going to have m r squared theta dot. And we interpret that as being the angular momentum of our point mass. Now, note here, theta is ignorable. So we can conclude that p theta, when we get done with all this, has to be a constant. It has to be conserved. All right. While we're at it, let's find pz. So pz will be equal to partial L partial z dot. So again, no z dots here, just there. And we get mz dot, which I don't think was a big surprise. That would be the z component of the linear momentum. So those are generalized momenta. So notice that despite the fact that we use the symbol p for both, the units don't have to match. So you got to be careful about that. All right. So let's go ahead and confirm that yes, indeed, that p theta is a constant. For pz, z is not ignorable. So we'll just note that. So we expect that we'll have some equation to solve for the z component. All right, well, let's just go ahead and do Lagrange's equations of motion on this. So partial L partial theta minus d dt of partial L partial, theta dot equals 0. So since theta is ignorable, partial L partial theta is 0. This will be minus, well, this we saw was m r squared theta dot. Differentiate with that with respect to time, we get m r squared theta double dot equals 0. So we get that theta double dot is equal to 0, and theta dot is equal to a constant. So in other words, yeah, in dd, the angular momentum is conserved. Okay, I don't think that was any big surprise. Let's go ahead and do the z motion. Partial L partial z minus d dt of partial L partial z dot equals 0. So there is a z in the Lagrangian. So I differentiate that. I'm going to be bringing down a 2 to cancel the half. So I'm going to have minus kz. And then for this bit here, the partial L partial z dot is just mz dot. Differentiate that with respect to time. That'll be z double dot. So minus mz double dot equals 0. Okay, so we have a second order differential equation. Let's go ahead and get into standard form. Z double dot plus k over m z equals 0. We look at that and go, my god, that is a simple harmonic oscillator. So that's omega squared. So what we get for the motion is that the particle orbits the center line at a constant rate while vertically undergoing simple harmonic motion. So it's kind of like tracing a sine wave out on the cylinder. All right. Make sure that we've got this down. Let's go ahead and do one more example. This one's a fun one. It's called the spherical pendulum. So once again, it's just literally a mass on a string. Difference is that we aren't pinky swearing to just let it move in a plane. We can give it some sideways motion now too if we want. And we do. So you can either like build a ring stand and attach the string onto the bob. That's one way you can do it. Or if you got like a big salad bowl and you have like one of those small little bits of soap that you ripped off from the hotel, wet it up a little bit and let her rip in the salad bowl. All right, either way, let's go ahead and put in a coordinate system. So this will be our z, this will be our x, that'll be our y. So we'll project this down into the xy plane, and that'll be one of our two generalized coordinates, phi, and then the angle off the z-axis will be theta. So if we think about it, yes, we've got one particle, so you would think you'd have 3 degrees of freedom, but since we're constrained to always be a distance L away from this point right here, that gives us a one equation of constraint, so that reduces our degrees of freedom to 2. So theta and phi it is, and that will do the job completely. All right, so in fact, we can just stick, well, anyway, let's go ahead and write the kinetic energy. So that would be 1/2, and let's go do the v dot v thing one more time just to get a feel for it. This time in spherical coordinates. So this would be 1/2 m. In the r direction, our velocity would have to be L dot, but by the constraint, that's 0. And then in the theta direction, we'll be going at L theta dot, so that's E theta hat. And then in the phi direction, that will be L phi dot sine theta times E phi, and then we dot that with itself. Doing that, we will get 1/2 m. Everybody's got an L that we'll have squared. Theta dot squared plus phi dot squared sine squared theta. All right. The potential energy, we can just up and write it. Mgl times 1 minus cos theta, and again, if you want to shift that 1 out because it's a constant, knock yourself out. Doesn't really matter when you differentiate it anyway. All right, so the Lagrangian will be t minus v. So that will be 1/2 ml squared theta dot squared plus phi dot squared sine squared theta minus mgl times 1 minus cos theta. All right, so the first thing that we can pull out of this is whenever you write a Lagrangian, you should just get in the habit of asking yourself, any ignorable coordinates? If there are, it makes your life go easier. So just ask yourself here, are there any ignorable coordinates? Yeah, phi is ignorable. So we can immediately get that the generalized momentum, p phi, remember that's partial L partial phi dot. Differentiating, this is the only term with the phi dot in it, bring down the 2, cancel the half, we'll have ml squared phi dot sine squared theta. That's a constant. All right. So, an analogy to stuff we've done before, we'll let this much of it right here, just the phi dot sine squared theta, will decree that that is the spin. So then we can write that my p phi is equal to ml squared times the spin. All right. And that's the only ignorable coordinate we've got other than the time. But that's not going to help us here. All right, so theta is not ignorable. So let's go ahead and write up Lagrange's equations of motion in theta. See what we get. Partial L partial theta minus d dt of partial L partial theta dot equals 0. All right, so partial L partial theta. Oh, we've got two terms with that. We've got this sine squared theta, and then we've got this cosine theta term. So let's tackle this one first. So because it's sine squared theta, when I differentiate that, I'm going to bring down the 2, right? Cancels the half. So I will have ml squared phi dot squared sine theta. And then I have to differentiate what's inside the sine squared, which is sine, so that gives me cos theta. Then d theta is 1, so yay. We're done there. Then let's see. This term here is plus mgl cos theta, but the derivative of cosine is minus the sine, so I end up with minus mgl sine theta there. All right, and that's everybody with the theta from this term. So now we gotta go hunting for any theta dots that might live around there. Oh, right there. So I differentiate this. The 2 kills the half. I'll have ml squared theta dot, but I have to differentiate that with respect to time. So I end up with minus ml squared theta double dot equals 0. Okay. Small favor, every term has an m in it, so let's just divide it out into the 0 and be done with it. Next step will be to put it into standard form, since we got ourselves a second order differential equation. So we've got theta double dot plus, I'm dividing through by L squared, right, in order to get in the standard form. So plus G over L sine theta minus phi dot squared sine theta cos theta equals 0. Now that looks horrifying because you go, oh my god, I've got that phi dot in there, that's horribly complicated. But remember, phi dot sine squared theta is a constant, right? So I can write my phi dot squared as the spin squared over sine to the 4 theta. So let's go ahead and make that substitution. So theta double dot plus g over L sine theta minus the square of the spin, which is a conserved quantity, cos theta over sine cubed theta equals 0. We'll be back to this guy. We'll call him star. All right. Now, that looks really ugly to solve. But maybe we can make some headway by first analyzing the limiting cases. Always a good idea. Maybe you can get some information from that. So let's look at some limiting cases. First one would be if we can find our oscillation to be in the vertical plane. If we do that, for that limiting case, phi dot would be 0, which implies that the spin is 0. So then star will become theta double dot plus g over L sine theta equals 0. And we know how to cope with that. That's a simple pendulum. So a bar of soap in a bowl is also a simple pendulum if you let it slide down vertically. Now let's say instead we gave it a nice little whack of initial velocity, and instead we are limiting the motion to be in the horizontal plane. So this is my first limiting case. My second limiting case, motion in horizontal plane. All right, so then we will be demanding that our theta be equals some constant theta naught. So then that means theta dot equals 0, right? Which is a constant. So that also implies that theta double dot equals 0. Actually, let's make those implications more explicit. All right. So if we plug in our zeros into here, right? Okay, so then that theta double dot is 0. And all these thetas are equal to theta naught. So this gives us something we can say about the spin that we require to orbit at that angle. So in this case, star becomes, putting in the 0 for theta double dot, we have g over L sine theta naught minus s squared cos theta naught over sine cubed theta naught equals 0. Oops, s squared. There we go. All right, so we can rearrange to get s squared. That'll be equal to g over L times sine to the 4 theta naught over cos theta naught. All right. But remember, s squared, or s, if we go way back, look at our definition, s was phi dot sine squared theta. In this case, it'll be phi dot sine squared theta naught at the point where we're evaluating that. So let's just put in for what that is. So we will be going at some speed phi naught dot squared. That'll be, oops, putting in for my s, and then squaring the sine squared theta gives me a sine to the 4 theta. That equals g over L sine to the 4 theta naught over cos theta naught. Oh, thank God, not as ugly as we feared. All those sine to the 4 theta naughts go away. And we worked this out some time ago, but it's just comforting to see that we are left with g over L secant theta naught for our phi naught dot squared. All right. So, and we could imagine that we might do some kind of motion that's utterly horrendous, but let's not make it horrendous. Let's say that our motion is just doing a slight perturbation around our theta naught. So if we go back and look at how our star will become there, so here's star again. So I'll copy and paste just to remember what star was. Excellent. So just rewriting that was star. Okay, so now we'll let theta vary slightly about theta naught. So if we do that, let's see here. We can write our, so we'll have theta double dot plus g over L sine theta. Our s squared we worked out is going to be, oops, did I drop a minus sign? No, I did not. Okay. So our s squared is going to give us a g over L, minus g over L sine to the 4 theta naught over cos theta naught. Then we're left with our cos theta over sine cubed theta. And we're demanding that that be equal to 0. So the trick we're going to do here is we've got a g over L sine theta and a g over L there. In fact, what I'm going to do is I'm going to make that g over L go away. And I am going to put that in parentheses to allow me to think about it better. All right, so since we're doing a slight oscillation about theta naught, it'll make sense for us to shift our coordinate system. So we're going to let xi be theta minus theta naught. All right, so we'll go ahead and, so if we recall our Taylor expansion, we can write our f of xi as f naught. So that would be when theta is theta naught plus f naught prime times xi. Oops, not zeta. Doggone it. There we go. Xi plus second derivative xi squared over 2 factorial plus and such. So we will let our f of xi be equal to our sine theta minus, well, the stuff in parentheses from up above. Sine to the 4 theta naught over cos theta naught, cos theta, sine cubed theta, right? So then we can recast our star what star has become. So this is our most recent version of star, right? We can recast it, noting that this c equals theta minus theta naught, the first and second derivatives of c and theta have to be equal. So we can rewrite star as c double dot plus g over L f of c equals 0. All right. So we're not going to worry ourselves too much here because we're promising that we're making small perturbations about the equilibrium angle. So we just need the first derivative. Getting the first derivative is a bit of a mess. So let's just go ahead and evaluate our f naught first. Oops. So our f naught for this expansion, that one's not so bad. That's sine theta naught minus sine to the 4 theta naught over cos theta naught times cos theta naught over sine cubed theta naught. Oh, awesome. Cancel, cancel, cancel. 3 powers, leaving 1 power. This minus that cancels, giving me goose egg. Super. All right. F prime evaluated at 0 is more of a chore. I will just assert that it actually cleans up kind of nicely and evaluates to 3 cosine theta naught plus secant theta naught. So, as long as we keep our c small, star has now become c double dot plus g over L 3 cos theta naught plus secant theta naught. C equals 0. And we know what that is. That's a simple harmonic oscillator, and this stuff here is omega squared. All right, so we can find the period of this motion, and then we can get some idea of how far phi would increase in one period of the orbit. So the period has to be 2 pi over omega. So it's equal to 2 pi times root L over G times the stuff in parentheses up above. So in one cycle, our phi after one cycle will be equal to our phi naught dot times the period. So we worked out that that was, our phi naught dot was g over L secant theta naught. Okay, and then this is L over G, 3 cos theta plus secant theta naught. Hey, all right, cancel, 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 cancel. Wish I could cancel that. We'll make it happen quick enough. So this will be equal to 1 over cos theta naught over 3 cos theta naught plus 1 over cos theta naught. Okay, multiply numerator denominator both by cos theta naught. I finally get it into 1 over 3 cosine squared theta naught plus 1. So that is the angle it will advance after one oscillation cycle. Okay, in the next video, we're going to tackle how we handle things if we actually do want to know the forces of constraint. That is called the technique of Lagrange multipliers.